We're going to look at the geometric properties of circles and triangles. So a textbook has given us this question here. It says find the length of this A. And the A is essentially the distance between the centers of these two circles here. Okay. The only information that this question has really given us is that the side length from here to here is 2.5 inches, it says. Okay. So this textbook has gone about making an assumption. In order for us to solve this question with only this information, we have to make the assumption that our circle, okay, is inside what is considered an equilateral triangle, which is a triangle that all three side lengths are the same. Now you can notice that this circle is tangent to 1, 2, 3 sides, okay? But we can also fulfill that with just an isosceles triangle, right? We have a circle inside of that triangle. It's tangent to 1, 2, 3 sides. And if this was the case, then we're kind of missing information. We don't have enough information to solve this. So let's go on the assumption that we are in what we would call case A. We're not working with case B. Okay, so in case A here, we assume that this is an equilateral triangle. All three side lengths are the same, which means all the angles within this are also the same. Okay, now we have to know some rules about this information. So I'm going to go over here, and I verified a bunch of stuff on a graphing calculator. And if you're very curious to do the verification, you can maybe pause the video now and go through a lot of our lines of points of intersection, our circle formula here. But if you just want to know the rule in the end here, I want to show you that 0, 0 is this point here, right? This is the bottom of our equilateral triangle. And our first point up, you'll see it disappear and reappear again, is 1/3 of the way. The height of this equilateral triangle that I've drawn, which is not the one in our example, is a √3, the height of it. Okay? And you'll notice that the center of the circle and the center of that triangle itself is 1/3 of the way up the √3. Hence I multiplied it. Okay? 2/3 of the way up, you'll see this coordinate. And that's the actual diameter of the circle within. So the circle within an equilateral triangle would be 2/3 its height. Okay? And finally, the third point is the actual height of the triangle. It's 1/3. So what that means is the space between this coordinate here and this coordinate here is 1/3 of the height. Turn back on. There you go. So that's 1/3 of the height, and the height of the circle is 2/3 of the height. So now that we know this rule, okay, now that we know this rule for a circle within an equilateral triangle, we can go back. Okay, so what does that mean for us? Well, that gives us a little bit more information. That means that from here to here, all the way down, that is 2/3 the height of this entire triangle. Okay, so we'll call the entire height here, okay, we'll call that h. And from here to here is 2/3 of h, which means the height from here to here. And actually, I've kind of got those drawn on a bit of an angle. Let's see if I can turn it a bit. I want those to be straight up and down. Hey, there we go. And maybe I should just rewrite it. There we go. So that it makes a little more sense. I don't want you to think it's the side length. It's the actual height is 2/3 of the height of the triangle, and this part here is 1/3 of the height of the triangle. So since we know that property, okay, we can use that to solve some other stuff. Now, keep in mind, if we were to build another circle, and we could continuously build circle upon circle upon circle within these spaces. We can keep zooming in, making smaller and smaller circles. You can make an infinite number of circles. But the next circle, okay, this one here, its diameter, okay, would be the 2/3 of the height from here to here. Okay, so that 2/3 continuously repeats over and over and over again. So now that we know that, we're to take our 2.5 information. So again, technically, we only know it's isosceles, but we're going on the assumption that it's an equilateral, so 2.5. What that means is we can find the actual height here, the height of this part of the triangle we can find. So we're going to turn this into a right angle triangle and use Pythagorean's theorem. Pythagorean's theorem is that c squared equals a squared plus b squared. Okay. Our c squared, the hypotenuse, is 2.5. Okay. And I'm going to write it as a fraction. I prefer to write in fractions just so we have a very exact answer in the end. If you want to use decimals, you can. So our c squared is 5/2. If we convert 2.5 to a fraction, it'd be 5 over 2. Okay? We'll call from here to here side A, and we'll rename B the h, so h squared will be what we're looking for. Side A is 2.5 divided by 2. Since it's equilateral, we're cutting it right down the middle, which means it's 5 over 2 divided by 2, and if you want to go through your fraction rules, that's 5 over 4 squared. Okay? So we need to isolate h squared. And when we do that, I'll bring our h to the left side here. Okay, which means I need to bring our other values over, but just know that it's essentially 5 over 2, and maybe I shouldn't do it that way. Let's keep it simple. I don't want to make it too confusing. Let's keep the h on the right. We'll bring our h squared over here. When we bring this to the other side, it becomes subtract. So we get 5 over 2 squared subtract 5 over 4 squared. Great. Let's keep going here. H squared is equal to 25 over 4 minus 25 over 16. I squared those two values. And to get h by itself, I actually have to find the square root of this side. Square root of. I'm going to change the denominators to both 16, so I have to multiply both the bottom and the top by the value 4. So we get 100 over 16, subtract 25 over 16. Okay, and that actually works out to the root of 75 over 16. Okay, 75 over 16 is this height here. But that's actually not the diameter of the circle. If you remember, the diameter of this circle is 2/3 of that height. So this value, to find the diameter of the small circle, so I'm going to call it the small circle, is 2/3 of our actual height, which was root 75 over 16. Okay. And again, the question is actually only asking for the radius. So the radius is, again, half that amount. So if I were to multiply, we'll call this now the radius of the small circle, 1/2 multiplied by 2 over 3 multiplied by that root 75 over 16. Okay, I can simplify the fractions in the front here. Write the rest in green, the radius of the small circle. We just do top by top, bottom by the bottom. That becomes 2 over 6, which is the equivalent of 1/3. Okay, so it's 1/3 of that height. That's the radius of the small circle. So we got that dealt with. Now the larger circle. Recall that information we talked about here, where we said that this is 1/3 of the total height, and this here is 2/3 of the total height. Okay, so let's keep this in mind here. We know that 1/3 of the height, okay, 1/3 of the height is actually, I'm going to do the equivalent ratios, is this value here, which is our root 75 over 16. Now, what we need to do is multiply by some value that would give us 2/3 of the height of the circle, right? Remember that this is 2/3. So we're trying to find like a ratio, a value where we can find out this height, multiply it by some unknown, we'll call it x, and that'll give us this part of the height. Okay, so we know it's 1/3 of it. So with that information, it turns out, okay, if we isolate here that the x value, if we use the number 2, 2 times 1/3 gives us 2/3. So in other words, we're going to multiply this by the value of 2, and that'll give us our height of this circle here, or this part, which is a better visual of it. So that equates to the diameter of the big circle. So diameter of the big circle. Okay, so I'll switch those two sides around. Diameter of the big circle is equal to 2 times root 75 over 16. But again, they're only asking for the radius again. So the radius again is half of that distance. So the diameter, oops, not the diameter, sorry, the radius of the big circle, is 1/2 times 2 times root 75 over 16. And 1/2 times 2 is just 1. We don't need to write 1 in. 1 times anything is just itself. So radius of the big circle is root 75 over 16. Great. We've now found those two radiuses. And remember, we have to add them together to find A. We can say that the distance A is equal to the radius of the small circle plus the radius of the big circle. And we have those two values here. So let's, there we go, plug them in. the a value is equal to the radius of the small circle, which is 1/3 root 75 over 16, plus the radius of the big circle, which is just root 75 over 16. Okay. Again, I like to work with fractions, so technically there's a number 1 in here, and I can change that to a 3 over 3. So now I'm just adding the two coefficients in front of here. Okay. If you want to convert these to decimals, just go right ahead and work with your decimals. My a value is then going to be equal to, when I add those fractions, 1/3 and 3 over 3 is 4 over 3 root 75 over 16. Okay. What does that mean as an actual inch or a measurement? We're going to convert it with our calculator. So bring up my calculator here. Plug in 4 over 3 times the root of 75 over 16. And that gives us a value of 2.886 repeated. So the distance between those two centers of the circles are 2.886. And just as a proof, I've graphed these out on a graphing calculator again. So again, if you want to pause and go through that relationship here, these are all the equations of the red circle, the purple circle. Again, they're in radical form, not actual, but the distance, those are the two centers. And if you were to subtract the values 4.33 and 1.443, you get roughly, again, because these are rounded, that answer we got in the other page on our calculator of 2.886. And there we go.